Okay. So that's basically about stacks. Like, we can use any registers. There is no restriction. The caller or the callee can use all registers. But the only thing is, when they are using certain registers, they have to make sure they are saved just in case the other side wants to use them. And then we have, of course, how do you encode an ISA, right? So you can have fixed instruction format where the size of every instruction is fixed. You can have variable instruction format. Intel is an example again of that. It has instructions varying in size from 1 byte to 17 bytes. Whereas MIPS is an example of fixed instruction format where all instructions are 4 bytes length. So now when we talk about opcode in the instruction of MIPS, we are encoding both the addressing mode as well as the operation in the opcode. And MIPS makes a very strong choice of having very few addressing modes. It has only, in fact, it has only two addressing modes, the immediate and displacement. And it constructs register indirect by making the displacement equal to 0. So it's able to mimic register indirect by making displacement equal to 0. And it also is able to get absolute addressing by using the base register of R0 with displacement. Okay, so it basically is able to get 4 addressing modes, but in reality supports 2 addressing modes. So that allows it to, capture the addressing mode and operation in the opcode very effectively. Now, coming to, register allocation, let me first talk about that because that's probably easy to understand. The question is, how many registers do we have? How many registers should we have in your architecture? The thing is that in the latest compilers, I believe, I'll only say I believe because, I haven't read compilers since my BTech. And I'm sure the compiler technology has advanced tremendously, like architecture has advanced. And unfortunately, even though I tried talking to the faculty who teach compilers in our university, none of them were aware of this. So I cannot update you on the latest because of that. Register allocation uses the graph coloring algorithm. I don't know whether you people are familiar with graph coloring algorithm. Are you?
Is it the one where you'll have to color the whole map without two colors being side by side, ma'am?
Yes. So no two adjacent nodes should be
Yes,
having
ma'am.
the same color. You should be coloring them with the minimum number of colors, of course.
Yes, ma'am.
Okay. That is basically what is used for register allocation. What do we mean by that? Which variables will be stored in the registers is done by using the graph coloring algorithm. Okay. So it's a it's something that I asked, like I said, I asked, but people are not familiar with this algorithm, how the register allocation is mapped to graph coloring, but and I obviously haven't had the time to explore it. But that's basically the thing. So to be able to do this, if you don't have sufficient number of registers, then graph coloring algorithm doesn't work well. So minimum 16 registers are needed for graph coloring algorithm to be effective. And up to 32 registers would be nice. Okay. we know that having more registers will mean more performance probably, right? Because you have the variables in the registers. And what is the thing that happens when you are executing code? You are basically fetching data, because we are talking about load store architecture, which is the most, highest performance architecture. We are going to bring variables from the memory into the registers and then operate on the registers. Now, supposing you are going to create a result operand, right? The way we do A, C equal to A plus B, then we say C is used, right? And maybe A and B are also reused in future and so on. Now, if we don't have sufficient number of registers, it is likely that we will have to overwrite that value in the register. And the next time it is referenced, you have to again go and fetch it from the memory. So every time we go and fetch something from the memory into the register, we are actually going to have a higher latency, right? So it is nice if all the variables that we need to operate on are in the register itself. Then you can, simply proceed with the, CPU will be able to access them immediately and proceed. So there is no waste of time, absolutely. So from that argument, it will mean that if you can have large number of registers, then you can have a much faster execution of your program. But what is the downside of having a large number of registers? If you look at the instruction formats of MIPS and any other instruction set architecture, the register value is actually part of the instruction, right? If you look at your MIPS I instruction, you have 3 register operands there. And if the more the number of registers, the more the bits that are needed to represent the register. So if you have 32 registers, you need 5 bits per, in each of the operands to represent the register which you are using there. So 15 bits are needed if you are having 3 register operands in your instruction. If you have 64 registers, then you will have 6 bits per operand. So the more the number of registers that you have, the more the number of bits you need in your instruction. Therefore, the instruction size increases, because of which your program size increases, and that also affects the performance. In fact, it reduces the performance of your code, because the larger the program, the more unlikely it will fit into the cache, right? So the performance of the program comes down. So you have to balance the need for more registers with, the size of the instruction. Any questions on that? Okay. So optimizations used by compilers. Okay, so the thing is that when compilers are doing various optimizations, and some of these optimizations are the most common optimizations done. So one, of course, if you have specified a macro or inline procedure, it is expanded. The compiler knows that it has to expand, so there is no issue. But the compiler also makes much smarter decisions about what procedures to expand based on its own analysis of the code. Okay. This happens pretty early. At that point of time, the compiler may not be completely sure of the size of the procedure. Okay. Then there is something called global common sub-expression elimination. So, we do many computations, right? And sometimes what we do, we have the same computation present in multiple locations. We don't store the computation in a variable, but instead we write this that arithmetic expression or the logical expression in multiple places. So what does the compiler do? It decide when it finds that there are these complicated, arithmetic operations which are there, which are not actually stored in a variable but are repeated in multiple places. It actually, creates a temporary variable, stores this value in that variable and uses that variable, and it allocates it to a register also if possible. So this, the compiler has to do a lot of analysis for this and decide whether this goes into the register or not and so on. Then, which variables should go to the registers, right? Which are the variables which are most commonly used. Based on that, we have to decide what of them, which variables will go into registers. Now, the loop unrolling, we'll see much more of it when we talk about both caches and instruction level parallelism. But instead of supposing you are saying for I equal to 1 to 16, so 16 times you're doing the loop. One way of doing that is, instead of saying 1 to 16, you will say 1 to 4. And within the loop, you will actually, write 4 statements. So supposing you're operating on an array of 16 elements, you will now loop for 4 times, but within each loop, you will operate on 4 elements of the array. Okay, so here we are unrolling the loop four times, right? Instead of 16 times looping, we are doing 4 times looping. The reason is because we are able to operate on 4 elements in each loop. This helps in very interesting ways, and we will see how it helps later. So these are some of the things that the compilers do, and they are done in certain phases, and these phases are fixed. And sometimes after doing a certain thing, the compiler may discover in the next phase that this was not probably a good thing to do because of certain architectural constraints. But the compiler unfortunately can't go back and undo those optimizations. So that those are some of the complications which arise, in the interaction between compilers and the architecture. So what can an architect do to help the compiler? That is the question that we have, right? Before I go there, any questions on the compiler optimization? So what can the architect do to help the compiler? One of the things that is strongly recommended is what is called as orthogonal operations or orthogonal behavior. So what do we mean by that? Supposing an addressing mode applies to a particular operation, it should apply to all operations. You shouldn't say, for add, I can use only register and immediate, but I cannot use register in direct addressing mode. So this sort of, differentiation should not be there. Then it's easy because anything can be applicable to anything. That eases the job of the compiler. Right? Otherwise, the compiler will have to check, oh, this is the operation. Is this addressing mode allowed? No, it's not allowed. So this is an error. This is that sort of complexity. As it is, compilers are some of the most complex pieces of code anyone can write. You don't want to make them more complex. Okay, so that is one thing. But one interesting exception to orthogonality is that there are special floating point registers. Okay, we are talking about general purpose registers. These are not used for floating point operations. When we talk about floating point operations, there are two things, I don't know if today they are still building the co-processors, but once upon a time, for floating point operations, they used to have a special co-processor which was built only for floating point operations. Now, this is not orthogonal. Similarly, the registers are not used for floating point operations. There are special floating point registers for those. So that is not orthogonal either. So when the compiler is allocating registers to floating point variables, it will allocate from the floating point registers. For other variables, it will allocate from the general purpose registers. So this it has to do. This is not orthogonal, but it helps a lot because it now allows you to double the number of registers you have without changing the number of bits you need for the register, uh, you know, um, registers in the instruction. So it helps in that way. Now, the other thing is provide primitives. Okay. Don't try to give an instruction which is specific to a language, special operation which may be in a language, or some kernel function which is very specific to one particular operating system. Don't try to give instructions corresponding to that. Give general instructions which are portable across all languages and all operating systems. Then this is a more complex thing which I sort of don't want to talk too much about. Simplify, because even the book doesn't clearly give about it. Simplify trade-offs between alternatives. Basically, it's like, there may be many different ways of um, doing the right thing. It should be easy for the architect to decide which alternative is more meaningful, right? So once upon a time, they would use less code size, for example, as a trade-off. Okay, especially because in those days the amount of RAM used to be very small. So having small code size was a good trade-off for the compiler. Okay, so when the compiler is deciding how to generate the code, it's the more importance was given to ensuring that the code is small in size. But that's no longer true because you are more interested in pipelining, and when you want to do pipelining, which is basically parallelizing the code, you will end up with more instructions but faster execution. So code size is no longer actually the performance trade-off. So it's very difficult nowadays to decide what to trade off exactly. That is one thing. Then the other thing is, if you know the value of something at compile time, no compiler wants to push it to runtime, because you can save time by binding the values at the compile time itself. Why should you waste execution time? That is one of the things that a compiler wants to do. So ensure that there are instructions available to bind such quantities to constants at compile time. These are the four things that the book talks about that the architect can provide to help the compiler write up. Okay. So in summary, what are the principles for instructions, instruction set? based on the statistical analysis of various programs, it is found that load store is anyway good for pipelining, minimizing the number of addressing modes which are most commonly used. Okay, and what are found to be most commonly used? Displacement immediate and register indirect are found to be most commonly used. So these modes should be supported. The common operations that are most frequently used are add, subtract, and, or, compare equal, compare not equal, compare less, branch and jump. So at a minimum, these should be instructions, right? And the operands which we use normally are 8-bit, 16-bit, 32-bit, 64-bit integers, and single and double precision, floating points. So those should be supported. Then if you want performance, okay, why are we saying performance? Because when you have fixed instruction encoding, it is very amenable to pipelining, which means that your performance will be much better. That is, your execution time will be faster. Okay. But if you are more worried about code size, when are you worried about code size? You're worried about it when you're talking about embedded systems, right? Embedded systems have a limited amount of RAM and the code has to fit into that RAM. There is no concept of virtual memory in embedded systems. So their code size is very, very important. It has to be as small as possible. When we are talking about that requirement, then variable and instruction encoding will give you smaller code size. So that is the option which you use. Okay, and how many registers do you need? For general purpose registers, a minimum of 16 is needed because the register allocation algorithm of the compilers requires at least 16. But if you have higher value, it is good. But having too high a value will mean that your instruction size will increase, therefore the code size will increase, and therefore the performance will go down. So, it's a trade-off, and that trade-off is done to ensure that you have good number of registers, but not too many. Okay. So that sort of covers, most of the principles behind instruction set principles. Now, the last section of this chapter is MIPS, which I am not talking about because the MIPS is covered in the videos. If there are questions, we can take them, but we assume that you know MIPS and we don't have to cover MIPS because the videos were put up long ago. Any questions? I know we are past the time. I don't think you have any class, I hope.
No class.
Yeah, if there are any questions on MIPS or the instruction set principles, I'll take them. Otherwise, the next class, I'll put up the videos for cache today. You can start looking at them. I'll also put up the assignment for the instruction level. Why am I saying instruction level? Instruction set principles.
Okay.
Because on Friday, we will be starting, the memory hierarchy. I'll put up the videos today. So there is, I'm going to put up in a certain order. It will be advisable if you see them in that order. I have 3 videos from one person and they are very simply explained, right? He talks about the memory hierarchy, which you are probably very much familiar with. Then he talks about a direct mapped cache and a set associative cache. and they are very nicely explained with good example of how the hit ratio improves when you use set associative cache. I think you have done these in COA, am I right?
Yes, ma'am.
Yeah, but it'll be a refresher probably for you. This whole chapter, I mean, at least part of the chapter is a refresher. The so the first three videos will be from one person. The first video is just a generic overview of caching. The next two videos, like I say, are for direct mapped and set associative cache example. Then after that, I'll be putting up two videos of Bhaskar and Raman of IIT Bombay. The third video, I'm still trying to figure out whether it goes into the next chapter or this chapter. So, but those two videos I'll put up. He also explains about the direct mapped and set associative and all that, but a little more in detail. In fact, much more in detail maybe, and very well done, those two. They'll give you a much deeper insight. The first three videos will be simpler. Bhaskar and Raman's will be a little more complex, but he has explained very well. So please go in that order so that it's a nice, gentle introduction to them. On Friday, we'll take up the memory hierarchy chapter.